welcome back. Today we get to talk about the matrix of a transformation. So last time, or maybe the time before, we saw that every single matrix gives us a linear transformation. And what we're going to see today is that if we're given a linear transformation, such as t from v to w here, and a basis for v, we can use that to then write down a matrix that describes t. So how are we going to go about doing that? So last time we saw something along the lines of, so since S is a basis, we can write anything in V, write any vector V within our larger vector space as some linear combination C1 V1 plus C2 V2 all the way down to n Cn Vn, where C1, C2 through Cn are scalars. All right, so that's the definition of being a basis, tells us that. All right, and then if we know what happens to each of these V1s through Vn, we're going to be able to know what happens to V. Again, hopefully we are remembering this. We did see this, but I want to refresh you. Okay, so T of V is the same thing. Well, let's just replace, we're going to take this step by step with the linear combination of the vectors in S. All right. And now T is a linear transformation, so each one of these plus signs here, we're able to split T up there. So this is C1 V1 plus T of C2 V2. Now formally what we want to do is use induction to prove that we can split up more than just one summand. Our definition of linear transformation says that you can split up at a single one. And it follows pretty quickly through induction that we can split up at every single one of our plus signs. All right. And then similarly, each one of these T of CV business has a constant, and that constant can come out. So we get C1 T of V1 plus C2 T of V2 all the way down to Cn T of Vn. Okay. So again, if we know what happens to each of these V sub 1 through V sub n, we know exactly what happens to V, because we just have to take our linear combination the same way with the n's. So let's go ahead and take this to an example so we can see a little more precisely what's going on. So let's go ahead and look at the example where T is a transformation from, let's say, three-dimensional space to two-dimensional space. No, let's bump it up. Let's go to 4. This will be fun. And let's say that we know, so S is a basis where we have 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's certainly a basis for R3. Hopefully we can agree on that. That's our standard basis. All right, and let's suppose that T of 1, 0, 0 becomes, let's see, we want some 3, 1, 4, 1. And T of 0, 1, 0, let's have be 1, 4, 1, 7. And 0, 0, 1, let's do -5, 0, 0, 2. Okay, so each one of these inputs a three-dimensional vector and outputs a four-dimensional. So cool, we've got the right domain and codomain. And let's go ahead and take a look. So if we want to figure out what x, y, z maps to, or maybe let's go with ABC. That sounds like more fun. If we want to figure out what ABC maps to, well, that's A times what 1, 0, 0 maps to, plus b t of 0, 1, 0, and c of t 0, 0, 1. All right, so that's a times 3, 1, 4, 1, plus b times 1, 4, 1, 7, plus c times minus 5, 0, 0, 2. Okay. Let's just complete this real quick. So 3a plus b minus 5c is our first entry. Our second entry is a plus 4b. Third is 4a plus b. And fourth is a plus 7b plus 2c. Okay. So we've gone ahead and we've figured out what this transformation does. But I want us to take a step back and look at this slightly differently. So this line right here, right in the middle, looks a lot to me like if we did some kind of multiplication. This is scalar times a vector, scalar times a vector, scalar times a vector. Okay. And what I see this as is that, let's see, how do I want to say this? Well, let me just flip this real quick to what our point is going to be today. So I'm going to put each one of these images in the columns of a matrix. So we have 3, 1, 4, 1, 1, 4, 1, 7, and minus 5, 0, 0, 2. Okay. And why did I choose to put them in columns like this? Well, let's think to our matrix transformations. So think matrix transformation. All right, from R to the N to R to the M. So we want A to be an M by N matrix. So if we look at our example here, it's going from 3-dimensional space, so N is 3, we have 3 columns, to 4-dimensional space, so we have M rows, 4 rows. And then, so each one of these columns, this is each one of the images from 1, 0, 0, 0, 1, 0. Oh, I'm a little off, aren't I? Okay, this is, well, I should erase that. Let's fix this. Okay, 0, 1, 0 goes to the last one. Oh boy, I'm saying not the words I'm pointing to. But anyway, so the point is we're going to take each one of these images, pop them in the columns because we want our columns to each have 4 entries because we want 4 rows. And we want 3 columns, which is how many things we're coming from. And let's go ahead and just test what happens if we multiply this by the vector ABC, kind of like we did above. All right. And what we get is take our first row times our column. Our first entry is 3A plus 1B minus 5C, which is exactly the first entry that we got above. Okay. Similarly, the second entry, we get 1A plus 4B plus 0C, then 4A plus 1B plus 0C, and 1A plus 7B plus 2C. All right, so we notice here that this is exactly the same thing as we had above. Okay, so this process in this second line here is essentially the matrix multiplication where we're putting our A, B, and C, our coefficients, in the column vector, and we're putting each of the images of our basis vectors in the columns of our matrix. So this is what we're going to be doing today. Again, we're going to be taking similar things to these blue arrows here, these big long ones that I messed up a few times, but ultimately got there. We're going to take these and we're going to put them in columns so that we can turn. So it turns out, so therefore, T is a matrix transformation. And the cool thing is that our result we see out of this, the cool thing we see out of this is that every single transformation from r to the n to r to the m, for no matter what m and n are, is guaranteed to be a matrix transformation through this construction. All right, so hopefully that gives you a hint for today, and have a good one. Bye-bye.